So today we will discuss vision transformers. Um, so the transformers were actually originally proposed for text kind of data, but eventually this was extended to images as well. So this is how the image vision transformer works. So given an image, typically a 224 cross 224 image, converted to patches of 16 cross 16. And each of the, so totally this will be converted to 196 patches or 196 tokens. And each patch is converted to an embedding. Converted to embedding. Embedding by using projection. So, and the rest of the transformer looks like a typical encoder of the text-based transformers. Right? So, which is nothing but we have the image tokens x1, x2, and so on, x196. And there is a classification token that is being appended. So each of this will go through a projection layer and we get embeddings for each of this. And they undergo something called as self-attention. And we get similar length tokens. This is where the mixing among the tokens happens. Now here we do this residual connection and followed by a layer norm. And after that, we give feed-forward network followed by residual connection and the layer norm. This comprises of one attention block. So typically, vision transformers have 12 layers of self-attention followed by the feed-forward neural network and 196 tokens along with the classification token. And final classification is done through the CLS, the representation of, let's say, 12th layer, and followed by the number of classes. So this is a typical vision transformer architecture. So we use only the encoder part of the text-based vision transformer. So how the inductive bias and the vision transformer is obtained. So this is not as CNMs, where the translation and variant property holds. So the vision, even though they don't have such a strong inductive bias towards the images, the vision transformer excels when the size of the data set is large. Vision transformers for large data. Some This is good for classification tasks, but which deals with the entire image. But if we want to do some level of detection within an image, object detection, some object in the image, then probably the vision transformer needs to be extended. So this is attained, attained by using advanced techniques such as shifted window transformers or spin transformers. So we can go over the notebooks and see the how vision transformers in practice it works. And yeah, So we'll now go through the notebook. Um, in this notebook, we implement the basic modules of vision transformers. So the first section, we import all the necessary tools such as dodge, numpy, and optimizers and datasets. Um, so first function is patchify, where we convert the images to patches. And the second is the multi-headed self-attention block, and default heads is taken to be 2, and D is the dimension of the token. And here in the attention, we implement the query key value. And so So typically, the self-attention block is given by this thing. Self-attention. So I'll explain the self-attention block for a single head. So if X is the input dimension of size token cross D, so the self-attention block is parameterized by query key and a value parameters. Right, so here we do the following transformations. So X times WQ, each can be assumed to be D cross D. Key tokens are obtained by like parameterizing by key matrix, and value tokens are obtained by parameterized value matrix. Now the mixing across the tokens happens via the dot product across each of these query and key. So mixing doesn't happen at this point, right? So there's no mixing across the rows of X. There's just combining the rows of WQ with the proportions of uh, each of the entries of the rows of the matrix X. So this is where the mixing across the tokens happens via XQ times XK transpose. So this is typically scaled with square root of D, the dimension of the token representation, and this is size of T cross T. And finally, the attention, self-attention output is obtained by taking the softmax across the rows of this mixing matrix XQ times XK transpose by square root of D, and this is multiplied by the value matrix. X. So this is token cross token dimension value matrices token cross D. And finally, we get an output matrix of token cross D. So this is what is being implemented in the notebook. So this is what is being implemented in the entire self-attention block. It's just multi-head. Each head is processed separately. And yeah, this is the entire ViT block. And this is where the residual connections are being added. And here we use the layer norms twice, once at the output um, of the self-attention and once at the output of the multi-layer perceptron as shown here. So this concludes the operation of one VAT block. And the entire VAT has several layers that is programmable. And this is what we show here. So the patchify part followed by linear mapper, converting the patches to the representations, and finally the tokens. And we add positional embeddings. And here the layers of the blocks is what is being implemented like this. And just we take the CLS token output and take the MLP and do the this, classification. So we use cosine style positional embedding. And the data set used here is the MS data set, training index. And here we convert these two data loader, train and test data loader, and we use Adam as an optimizer and the cross entropy loss with I minus 3 learning rate and box. And this is how it trains. And this trains for 2 epochs. And yeah, finally we got an accuracy of close to 70%. And this is a typical classification. This is our typical classification happens with the vision transformer. Uh, we again use the object detection based object detection using the transformer, right? And so this is typically this is the architecture of the transformer based object detection. So this is a positional encoding. So this is we use the CNN backbones and we get the image features. And this is transformer encoder. So this image patches being passed to the transformer encoder, and this goes to the transformer decoder. And finally, we have the prediction, each of the prediction heads here, and each of for this is supposed to classify an object in the class. There is a minimal implementation of the detection transformers. So you can see that the, the object is being detected as cat and with hand remote with pretty high confidence. So this is all regarding the notebook for this week, and we can move to the Q&A part now. So the question one is in the vision transformer architectures, which of the following design choices primarily helps in capturing the spatial dependencies across the entire image when batch embeddings are processed? And why is this method considered more effective than convolutional kernels in traditional CNNs for large-scale data sets? So, option A, the use of learnable positional embeddings added to patch embeddings, which enables the model to retain the spatial order of image patches even though the transformers are inherently permutation invariant. And option B is the multi-headed self-attention mechanism, which allows each patch to attend to every other patch in the image, ensuring global receptive fields that increase the model's ability to capture long-range dependencies. The layer normalization applied before multi-headed attention layers, which prevents the vanishing gradients and stabilizes the learning process, making it particularly effective for deeper network compared to batch normalization used in CNNs. The projection of image patches into a lower dimensional latent space through linear embedding layer, which significantly reduces the computational complexity and enhances the performance on large-scale image datasets compared to convolutions in CNNs. So the answer is B, which is nothing but the multi self-attention mechanism, where each patch attends to every other patch. It gives an important score to every other patch, and then linearly combines the tokens appropriately. So this ensures that receptive field is global at each layer of the transformer. And A is incorrect because positional embeddings ensure the model retains the spatial order, but they don't directly capture the relationship between the different patches. And layer normalization helps to training stability, it doesn't contribute to capturing the spatial dependencies. And linear embedding reduces compression but doesn't enhance the model's ability to capture the long range dependencies like self-attention. And coming to the second, so in the ViT model, an input image of size 224 cross 224 is split into non-overlapping patches of size 16 cross 16. So overall, we have 14 cross 14 patches. So each patch is flattened and linearly projected in the 768 dimensional embedding space. What is the total number of learnable parameter in this projection layer? So now each patch is flattened to 68 or 768 dimensional embedding space. And what is the size of each of this patch? It is 16 cross 16, that is 256. So it's 256 vector that is being projected into 768 dimensional embedding space. So uh, the linear projection layer flattens each of the patch to 256 pixel, uh, 16 cross 16 pixel patch to 256 dimensional vector and projects it into a 768 dimensional space. The total number of parameters in this projection layer is nothing but the multiplication of this 256 times the 768 um, dimensional vector. In the swing transformer architecture, the introduction of the shifted window attention is a key improvement over the traditional vision transformers. Which of the following is the primary advantage of the shifted window attention mechanism? It enables each window to attend to every other window across the entire image, improving the model's ability to capture global context without increasing the computational complexity. It allows the cross-window information exchange by alternating between regular and shifted windows across layers, improving both the local and global feature interactions without significantly increasing computation. It increases the window size dynamically at each layer, enabling the model to have larger receptive field without using multi-headed attention at initial layers, which significantly reduces computational cost. It eliminates the need for any positional embeddings in the model as shifted windows naturally encode the spatial relationship between patches, inducing the reliance on the additional layers for spatial understanding. So the true is answer is B because the shifted window attention alternates between the non-overlapping and overlapping windows, enabling the cross-window communication in computationally efficient manner. So this allows the local and global information to be captured progressively across the layers. And A is incorrect because swing transform does not allow each window to attend to every other window directly. They only attend to patches within a local window, and cross-window connections are made through shifted window mechanism. The model still uses localized attention in windows, but shifted window allows for indirect communication between the windows. The option C is incorrect because the swing transformers does not dynamically increase window sizes at each layer. The window size remains fixed, but the shifted window strategy helps capture global features across multiple layers. And is incorrect because swing transformers still use positional encodings to the provide the spatial information. The shifted window mechanism does not inherently replace the need for positional encodings, though it complements the spatial relationship across the learning process. So we are working with a swing transformer that processes an input image of size 224 cross 20 using a window of size 7 cross 7 for window-based self-attention. The transformer operates at four hierarchical stages with patch merging between each stage. Input patch size is 4 cross 4, and after each stage, the patch size is doubled, both height and width. How many windows will be created at the first stage of the swing transformer when the window size is 7 cross 7? After two stages of patch merging, what will be the number of windows at the third stage? Since the input image is 224 cross 224 and the patch size at first stage is 4 cross 4, this means the image is divided into patches of size 4 cross 4. So the number of patches in the first stage is 56 cross 56. And the window size is 7 cross 7 patches. Therefore, the total number of windows in the first stage uh, is 56 by 7. And times 56 by 7. So on an overall, we have 64 windows in the first stage. Now, after each stage, patch merging reduces the spatial resolution by a factor of 2 in both the dimensions. And after the first stage, the patch resolution is 28 cross 20. And after the second stage, the patch resolution is 14 cross 14. In the third stage, the number of windows with the window size of 7 cross 7 um, is 14 by 7 times 14 by 7, that is 2 cross 2. So in total, we'll have 4 windows. And the directional transformer model introduces novel approach to object detection by leveraging the transformers for direct set prediction without relying on traditional methods like anchor boxes or non-maximum separation. Which of the following best explains the role of bipartite matching loss in detection transformers and why it's crucial for models conversion? Forward and matching loss is used to minimize the distance between the predicted and ground truth bounding boxes by assigning each ground truth box to the closest predicted box, ensuring better localization accuracy for the overlapping objects. Parallel matching loss ensures that one-to-one correspondence between predicted and the ground truth objects by solving matching problem between the two sets, reducing the need for post-processing steps like non-maximum separation and allowing the model to avoid duplicate prediction. The bipartite matching loss dynamically adjusts the number of predicted boxes uh, during the training, allowing detection transformer to predict a variable number of objects in the image, which improves generalization to different complexes. Bipartite matching loss enforces strict spatial constraints on object predictions, ensuring that predicted access and non-overlapping, which eliminates the need for anchor boxes and improves the model's computational efficiency. So here the true answer is B because the bipartite matching loss injection transformer is used to assign one-to-one correspondence between the predicted and ground truth bounding boxes. It is achieved using the Hungarian algorithm, which solves a bipartite matching problem between the set of predicted objects and the set of ground truth. This process is crucial because it eliminates the need for post-processing steps such as NMS separation and ensures each prediction is matched to a unique ground truth object, preventing duplicate prediction. A is incorrect as the bipartite matching loss doesn't focus on assigning the closest predicted box to the ground truth box based purely on distance. Instead, it minimizes the overall cost. And C is incorrect because direction transfer always creates a fixed number of object slots which are matched to the ground truth objects. The number of predicted boxes are not dynamically adjusted. And D is incorrect because while detection transfer avoids anchor boxes, the bipartite matching loss does not enforce a strict spatial constraints or non-overlapping prediction. The role of matching loss is to handle assignments of prediction of objects, not to enforce spatial separation. In the segment anything model, which architectural choices allows it to generalize across different input prompts, points, box, mask for segmentation tasks. A multitask loss optimizing segmentation for all prompt types, a dense CNN backbone optimized for object detection, a visual transformer with a dynamic prompt encoder that adapts based on the input, unsupervised pre-training on millions of unlabeled images. To answer is C, which is a vision transformer dynamic prompt encoder that adapts based on the input. And segment anything uh, does not use multitask loss for prompt types. The model generalizes by adapting to different input prompts using the prompt encoder, not through a unified loss across the task. The SAM is not based on a dense CNN. Instead, it uses the vision transformer, which is more flexible and powerful for handling the diverse inputs, including a non-image data like prompts. SAM is not primarily trained on using unsupervised learning on level. It relies on large-scale level data for training and uses the dynamic prompt encoder to adapt across the task rather than relying on the unsupervised retraining.